Hello, and welcome to Lecture 5 of the Acceleration Unit in Phys 1104. In this lecture, we're going to take some of the ideas that we've been discussing and extend them to 2 dimensions. And in particular, that mostly is going to mean projectile motion, although I will introduce you to some other types of 2-dimensional motion that we'll look at much later in the course. There are certain things we have to be much more careful about in 2 dimensions than 1. For example, in 1 dimension, the average velocity and instantaneous velocity are usually in the same direction, or at least parallel. They can be in opposite directions. But in 2 dimensions, that's not even true, and let me show you why. So here's a very simple 2-dimensional motion. It's actually 2 straight line motions that are stitched together, and let's look at some average and instantaneous velocities. So here are 2 average velocities, the average from time 6 to time 7 and the average from 7 to 8. And let's think about the instantaneous velocity at time 7. Remember, that's how fast and which way is the object going right at time 7. Now from real data, this could be, for example, video analysis data that we're looking at here, we can't actually get the instantaneous velocity, but we can certainly approximate it pretty well. It ought to be roughly the average of v6.7 and v7.8, and we can be pretty sure it points down. Okay, now let's look at a different average velocity, and let me remind you that that is the velocity that the object would have had to go at constant velocity to end up in the same place. And you can get it directly from a displacement. So let's talk about the average from time 0 to 7. There's the displacement that you would get it from, and so we know that this average velocity points this way. And my whole point here is that these 2 vectors are not parallel. And in fact, if you think about it here, there is no instant when this object is moving in the direction of this v07. Even the shape of the path that an object follows in 2 dimensions can be tricky because it can depend on the perspective from which you view it. So here's an example. Suppose we have an object that's being dropped, and it's being dropped from a moving cart. The cart is going at constant velocity. From the stationary perspective, say this camera, which is firmly attached to the lab bench, the dropped ball follows a curved path. However, I've also attached a camera to the cart, and you can see that from the perspective of the camera that's riding on the cart, the dropped object falls straight down. And so the shape of the path that the ball follows depends on how we look at it. It depends on the motion of the observer. Well, counterintuitively, while that seems like it's very complicated, it leads to a simplification. And in particular, note that the view from the perspective riding on the cart is very simple. It's a nice straight line motion. And so the curved path from the stationary perspective perhaps can be understood better by thinking about that moving perspective. So here is the video analysis of the trajectory of the falling object blown up nice and big so you can see what's going on, and I'm going to use the velocity from 10 to 11 and the average velocity from 11 to 12 to estimate the direction of the acceleration at time 11. And so here are those vectors scaled up nice and big so that you can see the vector subtraction in detail, and we'll use them to get the acceleration that we want. So just as before, I'll take the negative of vi and add it to vf, and that gives me my change in velocity vector. And it points straight down. And so that means the acceleration at time 11 points straight down. And if I were to repeat that for all of the other times, I find that it's straight down at every time I look at. And what's more, I find that those acceleration vectors are all the same size. To see what's going on here, I want to remind you of something we've already seen, which is freefall. That's the motion of an object which is only under the influence of gravity. And we've seen that in freefall, the acceleration is constant, and it has a very specific value. It points down, and we can measure it, say, from v versus t data, and find the value of this g, which we call the acceleration due to gravity. And it's also sometimes called the freefall acceleration. Well, this explains what we've just seen. We've just seen that the acceleration points down, and if we look at the numbers, we would find that in fact the magnitude of that acceleration is just g. So this is free fall again. It apparently doesn't matter that the object isn't going straight down. It's still free fall because it's only under the influence of gravity. This often gets referred to as projectile motion, but really there's no difference between free fall and projectile motion. They're just both terms for the motion of an object acting only under the influence of gravity. And note that it is only a projectile from the moment of launch until the moment of impact, because before launch it had other things other than gravity acting on it, and after impact it also does. But between those times, the acceleration is g down, and so it's uniformly accelerated motion, but this is a two-dimensional version of uniformly accelerated motion. And so in particular, if we set our axes in the usual way, we can say that the x component of the acceleration is 0, the y component is negative g, but there's nothing preventing us from setting our y-axis pointing down, at which point the y acceleration is positive g. So now we know our acceleration components, and they tell us that the x component of the velocity must be constant, right? Because the x component of the acceleration is 0, and the y component of acceleration will have no effect on the x component of velocity. Similarly, it tells us that our y component of velocity changes at a constant rate, because ay is a constant. And the only other thing I'll say before going on to talk about equations is that this works for a projectile, but it works more generally for any object which is accelerating at a uniform rate in one direction. So for example, a hovercraft has no need to be facing in the direction it's going. And so if it's turned somewhat sideways and the propellers are producing a constant thrust, then that hovercraft will accelerate with a roughly constant acceleration in the direction it's pointing. The resulting trajectory would be just like a projectile trajectory. The difference would be that the acceleration wouldn't be g in general, and we could solve the motion by defining axes so that the acceleration points along one of our axes, it doesn't have to be the y-axis, and proceed as if it was a projectile. Let's check your understanding of these ideas so far. So we have an airplane and it's flying horizontally at 45 meters per second and it drops a package. And I want you to tell me about the velocity and the acceleration of the package just after it is dropped, the instant after it is dropped, and use the coordinate system that I've shown here on the diagram.